Hi guys, welcome to Unit 4 for the A-Level Computer Science exam, Processor Fundamentals. In this video, we're going to cover three subsections of Unit 4. The first is going to be on CPU architecture, the second is going to be on assembly language, along with a number of A-Level examples, and the third is going to be on bit manipulation. As a whole, this topic composes around 15 to 20 points on paper 1, so it's a fairly substantial portion of paper 1. We're going to get started with subsection 1 of Unit 4, which is focusing on CPU architecture, with the CPU, or the central processing unit, being the brain of a computer. In this subsection, we're going to start by learning what the von Neumann model is, take a look at the fetch-execute cycle, learn about something called register transfer notation, learn about different types of components that are part of the CPU, registers, interrupts, peripherals, and talk a little bit about the performance of computer systems. Let's get started with this section. The first concept that we're going to cover, and the foundational concept for this subsection, is going to be the von Neumann model. Now, the von Neumann model is the basis for all modern computers. So any computer that you may have used, including your phone, your MacBook, a desktop computer, they all follow the von Neumann model. There are a few other exotic types of computers that we're not going to get into at this moment, like quantum computers, that don't follow the von Neumann model, but odds are you're probably never going to use a computer that doesn't follow the von Neumann architecture. Now, some key features of the von Neumann model include a processing unit, which is like a CPU or a processor, the memory unit, which is the RAM in your computer, the random access memory, input and output mechanisms. These are methods by which data is input into your computer and then output from your computer. So for example, when you click using a mouse, you're inputting data. And when you're outputting data, you are displaying data on a monitor. So the ability to do this is a feature of the von Neumann model. Sequential execution. Now, sequential execution is the idea that when we have programs, and those programs are turned into instructions for our computer in binary, instructions are executed one by one in a sequential fashion. And then finally, we have the shared program concept. The shared program concept is the idea that instructions and data are stored in the same memory space or all together in RAM. Now, if we're talking about a Python program, for example, we're going to have instructions like print statement or arithmetic operations that direct the computer on what to do. And we're going to have data, like for example, the type of data that's stored in variables. And these are all going to be in the same program. Now, the shared program concept is the idea that the instructions for what the computer should do and the data for what those instructions are going to act upon are all stored together in the RAM in the same memory space. Now, to get a more practical idea of how the von Neumann model works, we're going to look at how a function, or how a computer that follows the von Neumann model functions. Now, right here, this basically shows a couple of different components, including the CPU and the RAM. Now, basically what happens when you open up any program on your computer is that program gets taken out of your hard drive. So let's say you want to open Microsoft Word. The information, so the data and the commands that go along with that program, are taken from your hard drive and then sent to your RAM. Your hard drive is also known as your secondary storage, and that holds all the data that's not currently being used. But the data for any programs that are currently being used are sent to your RAM or random access memory. So whenever you click a button to open up a program, you're sending data to the RAM. Now, while this is happening, our CPU is still functioning. So our CPU is our central processing unit. If we compare our computer to a brain, our CPU is basically your neurons. They're the part of your brain that makes decisions. Your RAM is your short-term memory for what you're currently focusing on, and your hard drive or secondary storage is going to be your long-term memory. So information that you might need later, but you're not currently making use of. So our CPU is constantly going through the RAM looking for instructions to execute and data on which to execute those instructions. Now, this constant process is actually driven by something called a system clock. A system clock is a separate component which isn't really seen here, but every second, that system clock, not every second, but every unit of time, and this unit of time depends on the speed of the processor, a signal is being sent to something called the CU. The CU is going to be the control unit. Now, the control unit is the device or the component in our CPU, in our central processing unit, that orchestrates the operations of all components within the CPU. If you think about an orchestra, the CU is the symphony conductor. So every unit of time, we get a signal sent to the CU, or the control unit. And what the CU does is send a signal to the PC. Now the PC is going to be our program counter. Now if you look at the RAM is actually set up like a table, and it's structured like this right here. It's basically a table with addresses and counters. And right here we see these addresses as integers 0, 1, 2, 3, 4, 5, 6, 7. In reality, they're stored as hexadecimal numbers that represent binary. But anyways, we have a bunch of data and instructions that are all stored in RAM, and they can all be accessed by going to an address in RAM. Now, in our program counter contains the address for the next piece of data or instruction that's going to be taken out of the RAM. And every single time our system clock sends a signal to our control unit, we're adding 1 to the address that's held in the program counter, meaning we're going to the next address in RAM. So for example, if our program counter has the address for 0 right here, the next time the system clock sends a signal to our control unit to move on, we're going to be looking at 1 in our RAM, and then 2, and then 3, and then 4. So the program counter contains the address for the data or instruction that we want to take out of the RAM next. Now that instruction or data is eventually going to be processed by our CPU. But anyways, when we get our next address for something to access in the RAM, we're going to send that address to our MAR. MAR stands for Memory Address Register. So we send the address to the Memory Address Register, and the Memory Address Register sends that address over the address bus to the RAM. Now the address bus is just a set of wires that connects our Memory Address Register to our RAM. We haven't really talked about the concept of registers yet. So let's take a deep dive into what registers actually are. Registers are basically memory storage. They're basically places where we can store data, and they're not very big. They're usually like 64 bits or 128 bits. They are faster than RAM. They're one of the fastest storage devices in your computer. Now the program counter, the memory address register, the MDR, a bunch of these different components that we'll see later on are all registers. The CU, which we've talked about before, is not a register. That is just a component of the CPU. So anyways, we're sending an address that we've stored, or that we've basically obtained from our program counter to our memory address register. And then the memory address register is sending that address to the RAM. And based on what is at that address, we're going to send the data or instruction from the RAM that we found back over our data bus to our MDR. Our MDR is going to be our memory data register. Now, once we receive that data, meaning what's in this column, at our MDR, we're going to send that data over the MDR, or over the data bus, to our CIR. Our CIR is another component called the current instruction register. And I'll just write that down right down here. Now, our current instruction register, that contains the data or the instruction that is really going to be processed by the CU. That's going to be executed by our CPU. It's the current instruction register, the piece of data or instruction that we're currently going to be executing using our CPU. And by executing, I mean taking action on. So for example, if we have a print statement in a Python program, we're going to be doing that print thing. So the CIR, once this data is in the CIR, it gets decoded. So that means that this instruction or data gets converted into a code format that can be executed by the CPU at the ALU. Now the ALU is the arithmetic logic unit. The arithmetic logic unit is responsible for any arithmetic or logical operations in a CPU or computer. This is really the component in the CPU that does the thing. It causes a window to open. It causes a print statement to be output. It's what actually executes the action. All the other components are basically supporting the ALU to be able to execute this action. The ALU is really the brain behind everything. So once we've executed some operation in the ALU, we're either going to reach back to the RAM to get some additional information, or to store some information in the RAM, or we're going to output to the monitor or to any other output device in the computer. Or we might initiate another action somewhere in the computer. But we're outputting the result, whether that be an action or another piece of data, from the ALU. Now, another register that we have is going to be called the ACC. The ACC really just stands for accumulator. Now, what the accumulator is it's sort of just a register where the ALU can store information that it's not using at the moment but needs to access later. So we can think of it as supporting the ALU in performing mathematical or logical operations. It's sort of a holding area for data that may be needed in the future. Anyways, that's how a von Neumann computer functions, or a computer that follows the von Neumann model. So first, we're clicking a button and we are opening a program, and all the data for that program is being stored in our RAM. While it's happening, the system clock is constantly sending signals to our control unit. Every time a signal is sent, the program counter increments by 1, indicating the next address in RAM to be accessed. Then, that address is sent to the MAR, or memory address register, from which it's sent to the RAM. We access the data in the RAM. That gets sent to the MDR via the data bus, that data gets sent to the CIR, where it's then decoded. Once it's decoded into another format, it's sent to the ALU to actually be executed. So if you want to number this, technically we're starting at the RAM. Technically we're starting at the RAM, and I guess while it's happening, we have the system clock sending a signal to the CU. So we'll just say the CU is number 2. Program counter, we're incrementing our address to the program counter. We're sending that address to the MAR. We're getting our data from the MAR, or we're getting our data from the RAM and sending it to the data bus, through which it gets sent to the MDR. Then it's at the CIR, then decoding happens. Then we send it to the ALU, after which we get output. And that's how a computer functions. So we call this the von Neumann model, but this is also called the fetch, decode, execute cycle, because we're fetching data from memory, decoding it, and then executing in our ALU. So to kind of list things out and give you a textual version of what happened, we can say that first the PC, or the program counter, increments and transmits the address for the next instruction to the MAR. The MAR sends the address over the address bus to RAM to fetch matching instructions from the RAM. Then our instruction is being sent over the data bus to the MDR. From the MDR, we go to the CIR, the current instruction register. And so the instruction sent to the current instruction register, but while it's happening, the system clock is telling the control unit to send a signal to the PC to increment by 1. So this is a cyclical process. Even while we're processing one instruction, another instruction is already coming into the pipeline. So we're already accessing the next address for the next instruction. Anyways, for the current instruction, whatever is in the CIR is decoded and then executed by the ALU. Now we might have something called an interrupt, which we'll get to later. And this is when we have some sort of emergency that the processor needs to handle. So it stops everything and handles the interrupt. But we'll get to that later. Anyways, that is the fetch execute cycle, also known as the fetch decode execute cycle. Now to see how this will pop up in the A-level exam, let's take a look at an A-level example. So right here, a process has one general purpose register, the accumulator, and several special purpose registers. We'll get into exactly what these are in future slides, but basically we have registers. Complete the following description of the role of the registers in the fetch execute cycle by writing the missing registers. The blank holds the address of the next instruction to be loaded. This is going to be the PC, or program counter. This address is sent to the MAR. We go from the PC to the MAR. The MDR holds the data fetched from this address. From the MDR, the data is sent to the CIR, or the current instruction register, and the control unit decodes the instruction's opcode. Opcode basically being operational code, or the code that denotes the instruction. And then once that's done, the PC again increments or goes up to the next address. We're adding 1 to go up to the next address. Now I wrote the acronyms here, but really you should write the full names. PC being program counter, MAR being memory address register, MDR being memory data register, CIR being current instruction register, and PC being program counter. Anyways, that's the fetch, decode, execute cycle. Now let's move on to some other components that are relevant to this cycle. However, before we move on to the other components in the CPU, one concept that we do need to cover is register transfer notation. Now, at the level at which this is covered in the A level, it's maybe a little bit pointless, but it's sort of a vernacular for communicating the different steps that take place in the fetch, decode, execute cycle. Now, there are 4 steps, and these are the only steps that you need to know. And basically, you can memorize all of these descriptions of each process. So for example, all of these, you can just go ahead and memorize them, and that's really all you need to do to answer any relevant questions on the A-level exam. Let's go over each one of them in detail. So let's start with the first one. Now, right here, we have the recipient of data being the PC or program counter, and we're taking the data in the PC and adding 1 to it. This represents the process in which the address in the program counter is incremented. So you've got the data signified by a square bracket, we're adding 1 to it, and we're storing the result in our program counter. And that is actually going to be one of the first processes that takes place in the FDE cycle. Now, the next process is not going to be, so this is going to be the next process. So here we're taking the data that's currently in the program counter, and we know it's data because we have brackets, we have square brackets, and we're transferring that to the MAR or the memory address register, and from there it goes to the RAM. And the idea that we're transferring data from the right side to the left side is signified by the direction of these arrows. Now next, after that, we have our third process. And here we are sending an address from MAR, and then based on that address, we're getting some data from the RAM. Now the idea that we're accessing data really in 2 locations is a reason for which we have double square brackets right here. So we're basically getting the data from the RAM via the address that's stored in MAR, and then we're transferring that to the MDR or the memory data register. And for our final process, we are taking the data that is in the MDR, or the memory data register, and transferring that to our CIR or current instruction register. As I said, all you really need to do is just memorize all of these different, not phrases, I don't really even know what to call these, I guess all of these different symbols for each process. So whatever we have in this column, you just need to memorize it and understand what each of them are doing, and that's enough. So if you look at a question that would be asked in the A-level exam with regard to register transfer notation, there are 2 errors in the following register transfer notation for the fetch execute cycle. Complete the following table by identifying the line number of each error, describing the error, and writing the correct statement. So if you look at number 1, we have the PC sending data to the MAR, which is correct. If you look at number 2, we have the PC getting the current data of the PC -1, which is definitely incorrect, because we're never going to subtract from whatever is in the program counter, we're going to add. So that's our first error. Next, we have data from the MAR going to the MDR. That's not correct because we're not sending data directly from the MAR to the MDR. We are getting it from the RAM and then sending it to the MDR. Hence, we should have double brackets. So this is our next mistake. And then we have data from the MDR being sent to the CIR, and that's fine. So we can say that on line number 2 and line number 3, we have a mistake. So for line number 2, our correct statement would be PC, and we're going to have PC +1. I guess statement is the correct word to describe these. And on line 3, we're going to have MDR, and we need to have our MAR in double brackets. And the description of the error is that for the first line, we decremented instead of incrementing. And I guess for line number 3, the description of the error, we would just explain what happens, like send address. So we can kind of just explain what's really happening rather than just trying to, I guess, even describe the error. But let's see what the mark scheme says, because I'm kind of curious about this. So yeah, I guess the description of the error is it should be the contents of the address in the MDR, or in the MAR. So by contents of the address, I mean the data that is referred to by the address, or the data that we get when we access the address. So I guess our answer is correct, but this is probably a better answer than what I wrote. Anyways, that's what you need to know in terms of register transfer notation. And this is an example of the type of question you'd receive on the A-level exam. Let's move on. Now registers are sort of at the center of the von Neumann architecture or the FDE cycle. I wouldn't say the center, but they're pretty important to those processes. So we're going to take a closer look at what registers are and how they work. So registers are small, fast storage locations. They may have sizes like 64 bits or 128 bits, which is significantly smaller than a hard drive or a RAM. They're also faster than RAM or cache memory, which we're going to talk about here in a second. Now, they're used to quickly store and access data, instructions, or addresses. They can have a variety of purposes. Now, these are some of the registers we've talked about and some that we actually haven't. So the program counter tells us what address we're going to access next. That memory data register holds data we've gotten from the RAM. The memory address register tells us what data to receive from the RAM. The accumulator helps us to complete arithmetic and logical operations in the ALU. And we have something called the index register, which we haven't really talked about yet. The index register is used to store and modify memory addresses while we're executing a program. So maybe we need to iterate through certain addresses, make some changes to addresses to access another piece of data in the midst of an operation. we're going to be using the index register to do that. And I think one of the reasons it's called the index register is it's often used for things like iterating through arrays. So in an array, we're going to have multiple locations in memory that are essentially adjacent to each other. And so in order to access subsequent elements in an array, we'd have to add 1 to a given address. So we start at the first element of the array, go to the address of that, and add 1 to get the next element, and so forth. And so that's the reason why index registers are used very frequently when iterating through arrays in programs. Now next, you have the current instruction register, which holds the instruction currently being decoded and executed. And then we have the status register, which is something else we haven't seen either. And this is basically a register that contains bits which are set or cleared based on the current status of the, not process, but processor. So what's currently going on in the processor? And this can include like what it's currently doing, the results of any significant arithmetic operations, and any errors that have taken place. Basically indicates what's going on in the processor at any given moment. So you should already have known all of these. The index register and status register are new, but those are things you're going to have to know as well. Now, we have an A-level question. A computer system is designed using the basic von Neumann model. Describe the role of the registers in the fetch execute cycle. And this is the same thing as the FD cycle, or fetch decode execute cycle, which we've been talking about. So we're going to go ahead and look at the mark scheme. And right here, this is a 5-point problem, right? Describe the role of registers in the fetch execute cycle. So what I'd recommend is writing 5 registers and then just describing what they are. Although in the mark scheme here, we have 1 register program counter, so we mention it and then describe it. 2, 3, I guess we did mention, okay, so never mind, we have the PC right here, and then 4. Now it says 1 mark per bullet point to max 5, but honestly, like, I would just recommend writing 5 registers. You could also have, I guess you have program counter, you could also have the accumulator as well, and just describe all 5 of them. Anyways, this is an example of where you would need to have a good understanding of what each of the registers in the FE cycle are, and any of the registers we went over in a previous slide, or in the previous slide. Now we have 2 types of registers, generally speaking. We have the general and special purpose registers. We haven't really seen any general registers, but special purpose registers are basically everything that we just went over in this slide right here. Now, general registers, special purpose registers, they don't just hold the status of a program. That's just one of many things they do. So kind of disregard this. We can just say that they do many things, but special purpose registers each have their own specific purpose. So they're tailored and used for a very specific purpose. So for example, all of these registers here are created to do 1 or 2 very specific things. And they can only be used by very specific instructions. We can only access and make use of them by giving the CPU very specific instructions to act on or make use of those particular registers. Or they might be instructions that are already a part of our CPU, but the point is they can only be initiated in a very specific way. Now, general registers, in contrast, are basically just registers that are sitting around the CPU that can be used for pretty much anything. We haven't seen these yet, but we will see them in when we're talking about assembly code, because oftentimes with assembly code, we're going to have to access registers to store data or addresses of other pieces of data. They can be used for any purpose by most instructions. They often hold temporary data or addresses while performing operations. So we haven't really seen any general registers because by their very nature, like, we're not going to give them a name, they're just general, but we will see them when we talk about assembly code. Everything we've learned so far has been special purpose registers. And the next component that we have is the immediate access store. Now I know this is blue, but the immediate access store is not a general purpose register. It's actually more of a concept, and it refers to a set of registers, cache memory, or other high-speed storage mechanism. So I can't really think of any other high-speed storage mechanism off the top of my head, but registers or cache memory are 2 pieces of memory that can be part of the immediate access store. Now we haven't talked about cache memory yet, but I guess let's go ahead and do that right now. So if you look at our current diagram, we don't see any cache memory right here, but cache memory is basically a type of data storage that sits between the RAM and the CPU. Oftentimes it can be in the CPU as well, but the point of our cache memory is that it basically stores frequently used instructions and data so that when the CPU wants them, we can go straight to our cache instead of going all the way to the RAM. The fact that we don't have to travel as far to get instructions or data means that we can get them more quickly, and therefore the processor can function more quickly. Now, the cache is slower than registers in terms of memory access speed, but it is faster than RAM. We have different types of caches like L1, L2, and L3 based on where the caches are located, but we're not really going to get into that right now. Anyways, that's what a cache is, because I mentioned it a couple of times, but I haven't really specified what it does. Anyways, caches can be part of the immediate access store, and what the immediate access store is it's designed for high-speed storage of frequently used data or instructions. So it's basically serving a similar purpose as the cache, but it may also use registers. It allows the CPU to immediately access data, and basically allows the CPU to function much more quickly. It's also volatile memory, meaning that it can be changed. So anyways, the immediate access store is really just a concept, and this is the idea that we have some high-speed memory in our CPU that allows us to more quickly access data or instructions. And the cache does this, and it's a part of the immediate access store, but other registers can also be part of the immediate access store. Now, the next concept that I want to talk about that we haven't really talked about so much is going to be the address bus, data bus, and control bus. We talked about the address bus and data bus briefly, but we never talked about the control bus. Now, the address bus basically allows the MAR to communicate with the RAM. So whenever the MAR is sending address to the RAM, that's going to be via the address bus. When data is returned to the MDR from the RAM, that's via the data bus. An MDR can also be transmitted to the control unit via the data bus, and oftentimes if the ALU needs to access the RAM, that can be through the data bus as well. So the address bus is actually unidirectional. We're only going to be sending data one way from the MAR to the RAM. But the data bus is bidirectional because we can have data going both ways when we want to access some data in the RAM or transmit some data to and from the RAM. Now, the final bus that we haven't talked about is the control bus. The control bus can transmit interrupt, timing, read, or write signals. Basically, the control unit controls everything that's going on in the processor and the CPU, and the control bus is what controls the CU to all the different components in the CPU. So really, our control unit is going to be what's in black. It's basically controlled to everything in the CPU. I mean, it controls everything. It controls every component, so it needs to be connected to every component, and that connection is done by the control bus. It allows the control unit to control and coordinate the operation of various components in the CPU, and it takes advantage of bidirectional communication. So it'll send commands, but also receive feedback from other components so that it can make further decisions on how things should work in the CPU. Now, the next component I want to talk about is going to be the arithmetic logic unit. We talked a little bit about this. This is not a register, but this is basically like really the component in the CPU that does the thing. It really solves the problems, it performs logical operations. Everything else kind of supports the ALU in allowing actions in the computer to take place. We can refer to it as the processing unit of the CPU, even though the CPU is called the central processing unit. More formally, it's responsible for arithmetic and logic operations, and any really mathematical or decision type operations for currently running software. It processes decoded instructions sent from the CIR, and it represents a core. So if you've ever heard of dual core or multi-core processors, each one of those cores is actually an ALU. We'll talk more about this whole idea of multi-core processors in future slides. Now that we've talked about the ALU, let's talk about the conductor of the so-called symphony that is the CPU. Now this is the control unit, and the control unit works in tandem with something called a system clock. We briefly referred to this early on. I think I referred to it as a timer actually, but basically the CPU is operating every second or every unit of time. So it operates on a regular interval, to be more specific, not every second. And this operation at a regular interval means that we can have sequential operations. So we can interpret and we can execute instructions one by one. It's sort of essential to the control unit and the CPU in general operating in a way that doesn't allow different operations to clash with one another. Now the system clock gives out timing signals at regular intervals. This controls something called clock speed, which is the pace at which processors process instructions. Now these timing signals are sent to the control unit. So the control unit can initiate operations in the CPU at these given intervals. Basically, the control unit initiates data transfer to and from data storage, which is the RAM or cache, etc. And it generates signals that are sent on the control bus to other components at the regular intervals that are dictated by the system clock. It orchestrates the overall functioning of the CPU as we talked about before. Now, again, via the system clock, all these are happening at regular intervals, which are represented by a clock tick. And at each of these intervals, each of these ticks, we have a single instruction being executed. This could be a single instruction. This could be some sort of data transfer, something in tandem with data. But the point is that fetch execute cycle is going to be executed each time the clock ticks, each regular interval. And this synchronization is absolutely essential for the operations of the CPU. So right here, we have a diagram of a control unit. This is our clock. So our clock is sending its timing signals to the control unit. And the control unit is based on those timing signals and other things like flags, and based on the instruction register, which is feeding the control unit instructions to be decoded and sent to the ALU. The control unit is sending its own signals out to the control bus. So we have different signals that are being sent to the control bus to control operations in different parts of the CPU. Okay, so now let's take a look at something called interrupts, which we briefly touched on earlier. Basically, an interrupt is when we interrupt the fetch execute cycle. So we interrupt the processor. Now, there are a number of reasons we might do this. So some causes of interrupts include hardware issues. So for example, maybe you're working your computer and your printer jams. This is sort of like a sudden event that needs to be handled. And therefore, this will lead to an interrupt in the operations of the processor so that a window can be opened and a warning can be issued to the user, for example. In terms of software, we might also have interrupts when our program is looking for a file that can't be found, division by zero, array index out of bounds, or any other errors. This will interrupt the operations of the processor, sending us a warning or taking some other action. User intervention could be another way. Whenever we hit Control-Alt-Delete or force quit on a Mac, these are both instances in which the processor is interrupted to allow us to execute some other operations. External events, different from a printer jam, I guess. So whenever someone types something into the keyboard or clicks on a mouse, or we have incoming network packets, so we've requested something and we have something coming back over the internet or the network, this could lead to something that might interrupt the processor. Now, keyboard inputs might be Control-Alt-Delete or something similar, and mouse clicks, that could depend where we're clicking or what we're doing. Furthermore, input-output processes could be another instance. So maybe we've, for example, if you ever plugged in a USB drive and you've sent data to it, when that data has finished being transferred, you might receive a pop-up window. That's going to be done through an interrupt. And finally, timing signals. Now, these are the multiple causes of interrupts, and these are used to deal with events that require immediate attention. Now, these interrupts can have different priority levels. So, for example, a blue screen of death, that's being caused by an interrupt, and that's going to have a much higher priority level than, for example, the completion of a data transfer. So different interrupts, depending on the extent to which they affect the computer's operations and the processor operations, will have different priority levels. And these dictate how quickly those are handled by the processor. Now, interrupts actually replace something called polling. Polling is where a processor would constantly ping different parts of a computer or constantly send messages to different parts of the computer waiting for a response. This is very inefficient because this means that the processor is constantly devoting resources to communication with different aspects or different parts of the computer, even when there's absolutely nothing going on and there might not be anything that will happen. So polling is kind of just waiting for something to happen, versus an interruption is a signal that only occurs when something has actually happened. So it's a lot more efficient, a lot more asynchronous than rather than polling would be. So how do interrupts actually work? Well, let's take a look at how they work in the context of the fetch execute cycle. So first, if we have an interrupt, that interrupt is detected and the priority of the interrupt is checked. Is it high priority or is it low priority? If it's lower priority, we're going to finish our current execution of the fetch execute cycle. So we're going to finish processing the current instruction and then deal with that interrupt. Otherwise, if it's high priority, we're going to store the state of the current process. So everything going on in the current process or in the CPU at the current moment is going to be stored in a stack. And then we're going to go ahead and deal with that interrupt. By dealing with the interrupt, that means we're going to identify the type and location of the interrupt and call the corresponding ISR. Now, the ISR is the interrupt service handling routine. Every different type of interrupt has one of these, and these are basically software that allows us to deal with the given interrupt. When that routine is finished dealing with the interrupt, we're going to check for any other higher priority interrupts or high priority interrupts and deal with those. If there are none, we're going to load that data that we stored from the process in the stack. So that data that was for the operation that we interrupted, we're we're going to take that data back out of the stack and then continue with our process. So basically, detecting the interrupt, we are dealing with the processor. So we're either finishing our fetch execute cycle or storing the current information or the information for the current process, identifying the location or type of the interrupt, calling the appropriate interrupt service handling routine, dealing with the interrupt, checking for any other high priority interrupts, and then going on with our day. So loading data from the stack and continuing with the process, or just continuing with our current program. So we have a related A-level question. Describe when interrupts are detected in the FE cycle and how the interrupts are handled. Now this is a 5-point question. We need to talk about how they're detected and how they're handled. So we're going to go ahead and look at the mark scheme. They're detected at the start or end of an FE cycle. Now this is the answer, but really interrupts can be detected at any time during the FE cycle. However, this is the A-level answer, so this is what you're expected to write. Next we have our explanation of how they're handled. So you're basically what I just went over: priority is checked, do different things based on lower and higher priority, and then store the state of the current process. If it's high priority in a stack, this is going to be stored in a register, identify location, ISR, when ISR is finished, return to step 1. So just start all over again and deal with any other, if you don't have any high priority interrupts, deal with any other interrupts. Otherwise, continue with the process. Anyways, this is the only one that's sketchy, so this is something I would keep in mind. Really, the point of an interrupt is it can happen anytime during an FE cycle. Now we're going to move on to a set of topics that are a little bit more out of left field, in the sense that they're not really related to what we've done before. They're basically ports and ways of connecting to computers, and then later on, computer performance. So the first type of port or method of communicating with the computer we're going to talk about is going to be USB, or Universal Serial Bus. Now this is a pretty standard method. You connect mice or mouses to your computer and a variety of other devices using USB. You've definitely seen this before right here. Now, some things you need to know about USB is that when we're connecting a device using USB, 1 bit is transferred at a time between that device and the computer. We can have synchronous or asynchronous transmission. So that means that data can be transmitting at a steady rate, where transmission of data is synchronized between the computer and the device, or it can be more reactive. So at random times, based on what's happening in either the device or the computer, there is communication. USB 3 transmission is kind of the current standard. And what USB 3 transmission indicates is that there's two-way communication, where both the sender and the receiver, the sender being the USB device and the receiver being the computer, can simultaneously send messages to each other back and forth. In the case of many more complex devices, this might be something like data packets or electrical signals. In earlier USB versions, only half duplex communication was possible. So two-way communication between the computer and the device, but not simultaneously. Now, one of the big advantages of USB is that USB devices can be automatically recognized by computers, which then loads the corresponding device driver. So if you plug in a device to a computer, it can recognize it and then access the driver, with the driver just being a small software program, to then enable you to be able to use that device. Now, the next connection method we're going to talk about is going to be HDMI, or the High Definition Multimedia Interface. If you've ever tried to connect a TV to your computer, or even a monitor nowadays, you've seen HDMI cables and worked with HDMI ports. These basically allow audio and video transmission. It allows you to output audio or video from a computer to a display device. The audio video data is digital and it's high definition. And it's basically a digital replacement for VGA, which is something we're going to look at next. But in short, HDMI is a way to output audio and video to your computer. Now, VGA is Video Graphics Array. You might have seen this before if you've worked with an older computer, but we don't really use VGA as much. HDMI is kind of the standard now. And whereas HDMI was a digital method for transmitting audio-video data, the VGA is an analog method. So it was introduced in the late 1980s, and it has a lower refresh rate, meaning that the image on the screen is changed less frequently. It has fewer number of pixels, which means that the definition of images isn't as good as HDMI, and the number of colors are fewer than HDMI, which means that we can't represent the color images to the extent that we can with HDMI. So now that we've talked about ways of connecting to computers, we're going to move on to performance. Now, this is specifically the factors that affect the performance of a computer in terms of the speed, at which they can process and deal with programs. The speed at which they can execute programs, more specifically. Now there are 4 factors we're going to talk about. The first is the number of cores. The second is the bus width. The third is the clock speed. And the fourth is the cache memory. Now, number of cores refers to the number of ALUs in a processor. So if you look right here, in our previous example, we only had one ALU. So we really only had one device that was actually executing operations with data that came from the RAM. Having additional cores means having additional ALUs that are all working in tandem. So each core can independently execute instructions, which means that there are multiple cores working to execute instructions at the same time. Now, I think you've probably come across the terms dual core, quad core, 16 core if you've ever been to any computer shop. So typically typically CPUs have cores in multiples of 2. So you're not really going to have like a tri-core CPU. It's usually just going to be, again, multiples of 2. Now, while number of cores can significantly speed up the operations of your computer and different programs, there are also some factors that can slow down how quickly they work or how quickly they're able to execute programs. So first, you do need to have communication between cores. So cores need to be able to communicate each other to efficiently complete tasks. And this can add overhead. This can require some additional processing power or the use of additional memory. The point is that if you have 2 cores, that doesn't mean that the speed of your computer, the speed at which you execute programs, is necessarily going to be twice what it was before, or twice what you would have with 1 core. You also need software to be specifically utilized or specifically designed to utilize multiple cores. So if software hasn't been designed to actually make use of multiple cores, processing its instructions in parallel, then there's almost no point to having multiple cores at all. And finally, memory access speed may bottleneck operations. So you might have multiple cores that are ready to execute operations or execute instructions coming from the memory. But if you can't get enough instructions from the memory fast enough, in order for all of the cores to be able to continually process instructions, then it doesn't really matter. And you're going to have some cores that aren't doing any work at all while they're waiting for additional instructions to come from memory. Overall, one of the biggest advantages of the number of cores is that more instructions can be carried out simultaneously, but this depends on a number of factors. Now next we have bus width. So this refers to the number of bits that can be transferred via the address bus, data bus, or control bus. So remember, in our fetch execute cycle, we were sending bits of data, we were sending addresses to the RAM, and then we're transferring data and instructions. We're sending addresses to the RAM and transferring data and instructions back to the MDR. Now we were doing that through buses. Now the bigger these buses are, the more addresses or the larger addresses that we can send to the RAM, and the more data we can send back, which is just going to increase the speed at which the CPU is able to pull data off the RAM, and therefore the speed at which it can actually execute instructions. The control bus can also play a factor. It can also be enhanced by being larger, by having more bits that are transferred. Because of the fact that means that we can send more instructions at a quicker rate to different components. Now to be clear, bus width means that the address bus, the data bus, or the control bus are bigger. They can transfer more bits at any given point in time. So they're wider, we could say, hence bus width. And overall, the result is increased speed of memory access and therefore an increased speed at which the overall computer system operates. Now next we have clock speed. So clock speed is the number of fetch execute cycles that can be conducted per second. So the number of cycles that can be executed per second is actually measured in hertz. And hertz is also used for talking about waves. I think it's like a wave frequency. Anyways, if we have a 2.1 gigahertz computer, then that means that 2.1 billion fetch execute cycles are being executed per second. Now, I mentioned this statistic because this kind of puts things into perspective, and odds are you've probably heard of clock speed. So if you've ever gone to a computer store again, it's usually advertised that, oh, this computer has a 3.2 gigahertz processor or a 2 gigahertz processor or whatnot. But that's what that means. Now, one thing to keep in mind is due to the hardware and software constraints we talked about before, if we have additional cores, that doesn't mean we're going to have perfectly multiple clock speeds. So for example, if we have a 2.1 gigahertz dual core processor, that doesn't mean that we're going to be operating at the equivalent of a 4.2 gigahertz clock speed because of things like communication between cores, the bottleneck that memory access presents. And additionally, there's one other factor. That was the fact that software needs to be able to utilize multiple cores. Anyways, overall, we can say that a higher clock speed means more instructions that can be executed per second, and hence can lead to faster operations of the CPU and the computer. This is just an example of some statistics we might see from the performance of a computer. Like this is from a computer with a CPU that operates at 2.2 gigahertz. Or actually, I guess 2.8 gigahertz. 2% of it's being utilized. There are 100 processors running on it at the moment. I guess it's weird because it says that its maximum speed is 2.2 gigahertz, but it's probably being something called overclocked. Overclocked means running the processor at higher than its designed limit. So I guess it's running at 2.8 gigahertz. And it says there are 4 cores and 8 logical processors. Not really sure why that is, but it sounds like a pretty hardcore processor. We can also see some examples of caching. So we have L1, L2, and L3 cache, and they each consist of a certain amount of memory. Now the last factor we're going to talk about is going to be cache memory. We already talked about cache memory right here, the L1 and the L2 cache. Now what these do is these sit between the CPU components and the RAM, and they hold frequently used instructions or data. As we said before, because the CPU doesn't have to go all the way to memory to get certain pieces of data or instructions, it actually increases the speed at which it can operate because it has the instructions and memory sitting closer to it and in cache memory, which is faster than RAM. So that is the last piece of, that's the last performance factor when talking about how quickly computers work. Now, what I want to do before we move on is talk about or look at an A-level question that is based on the idea of performance. So describe 2 ways the hardware of a laptop can be upgraded to improve the performance and explain how each upgrade improves the performance. Now we're going to go ahead and look at the mark scheme just for some examples. And one is increasing the number of cores. Another is increasing RAM capacity, which we actually didn't talk about before. But the more RAM that we have, the more space we have to hold currently running applications. This means that we don't have to go to our secondary storage. So we don't have to get any data from our hard drive, which is much slower. So the more we can have in RAM, the less we need to access our hard drive, and hence operations will be faster. We can also increase cache memory, which we talked about, and then increase clock speed, which means that more fetch execute, or we can also call these fetch decode execute cycles will run per unit time. Now let's move on to subsection 2, which focuses on assembly language. In this section, we're going to talk about what assembly language is, instruction groups, assembly stages, and addressing modes. We're also going to be solving some A-level questions, with that being the focus of this particular section. Keep in mind that we're not going to have to learn how to write code in assembly language, just how do you trace and understand code. First off, what is assembly language? So assembly language is a programming language that is tailored to a specific type of CPU. In general, assembly language may not only be used in the context of computers, but also in the context of smaller chips or processors. With assembly language, we get more direct control over the CPU than if we were just using a regular high-level language like Java or C++. We can directly access the register and other components of the CPU. Because of this, code in assembly language is highly efficient. It's often used for performance-critical functionality. So it's used for software where the speed of the software is absolutely important, where it needs to be running as efficiently as possible. So what we're going to do now is take a look at what assembly language actually looks like. Now, regardless of how effective assembly language is, at the end of the day, it's going to be translated into binary before it can be interpreted by the processor, by the ALU itself. So right here, here's an example of assembly code or assembly language. So each assembly instruction corresponds to specific binary code that the CPU understands. So here we have add, that's going to be a command in assembly, and we're going to add 45. So we're going to have an add command, that's going to be our code, our actual instruction, and the data that instruction is going to be operating on is going to be 45. So this is really what that code would look like. Now, if you look at the next slide right here, we can see different other assembly examples of assembly along with the machine code that they correspond to. So all assembly code is going to be easily translatable to machine code. And for example, right here, this load command, this means load the value 2 into the accumulator. The store command means store the value of the accumulator in memory location 13. And there are a bunch of other commands that we're actually going to look at in some depth later on. But I just wanted to show this to you as an example as to what assembly code looks like and how it's interpreted how it's converted and then interpreted by the ALU. So basically, the fact that assembly code is going to be translated into machine code. As I said earlier, you're not going to have to be able to write assembly code, but you are going to have to be able to understand what assembly code does and some of the concepts surrounding assembly code. So the first concept that we're going to talk about is going to be the concept of instruction groups. Now, instruction groups are basically just categories of the different types of instructions or commands that we can write using assembly language. The first one is data movement. So commands associated with data movement allow us to transfer data between registers and memory, between registers and accumulators, between memory and accumulators. So really between registers, memory, and accumulators, we can just move data around. Here's some examples of data movement related commands. The first one is just a command that loads the number n into the accumulator. So for example, we might have a command like this, and that would just put the number 53 into our accumulator. Or another command might be this one right here. So from the address, whatever's in the address that's specified right here, and the contents will be added to the contents of the index register, and then those contents will be stored in the ACC. So for example, we might have like LDX, and then an address that perhaps looks something like this. Ordinarily it'd be hex, but whatever, hexadecimal, whatever. Now we're going to add this. We'd add 365 plus whatever is in the index register, and then that would end up getting stored in the ACC. Now another command could just be this one right here, which would take the contents of the ACC, so whatever's in the accumulator, and just put it in the address it's specified. So it might look something like this, where 453 is the address, and whatever's in the accumulator, it would put it at that particular address in RAM. Remember, whenever we're referring to address right here, we're talking about a location in RAM. So those are examples of data movement commands. Now, the next category is going to be the input and output of data. And these are basically instructions that allow the user to input data from a peripheral like a keyboard or output data to a screen. Here's some input and output commands. So right here, key in a character and store its ASCII value in ACC. Basically, we would type in, this would give us the opportunity to type in some values using a keyboard, and the result will be stored in the accumulator. Or output to the screen the character whose ASCII value is stored in the ACC. So this would allow us to output the contents of the accumulator to the computer screen. Kind of like a print statement in Python. Next, we've got arithmetic operations, which basically are what they sound. They allow us to perform mathematical operations on data stored in the accumulator, and then we can go ahead and take the result and store it back in the accumulator in most cases. So here's some examples. We have the add command. Now the add command might look like this, where 373 is an address. And then basically what we would do is we would add whatever is at this address in RAM to whatever is in the accumulator, and then store the result back in the accumulator. Another command might be the inc. So right here it says add 1 to the contents of the register, ACC or IX. So for example, if we did inc IX, that means whatever is in the index register, we're just going to add 1 to that. These are just some examples of arithmetic operations that we can initiate using assembly language. Now the next two instruction groups we're going to look at are going to be the comparison instructions and the conditional instructions. These kind of go hand in hand. What comparison instructions allow us to do is compare the contents of the accumulator with some other value to see whether they're equal or not. And based on whether they're equal or not, then we can execute a conditional instruction. So if we actually look at the code, right here we have some examples of comparison instructions. We'll look at the most simple, which is CMP hashtag. So if we have CMP hashtag 3, that means we're going to check whether whatever is in the accumulator is equal to the number 3. Now, if they are equal, then we can basically do one thing. So if we want to initiate some action when 3 is equal to whatever is in the accumulator, then we need to specify a JPE command. This is a conditional instruction, and that's going to allow us to jump to a specific address. So if we want to specify that when 3 is equal to the contents of the accumulator, we want to go to address 205, this is how we would do it. Only if this is true will this JPE command, or this JPE instruction be executed. However, if they are not equal to each other, then we would do something else. So we'd have CMP3. And if we only want to initiate an action when they're not equal to each other, we would have to use our JPN command. So JPN can only be used to jump to an address if the previous comparison instruction is false. So we'd have JPN, and then we might have 210, meaning that we're going to go to 210 in memory. So this means that we're going to go to location 210 in memory, and then either access whatever instruction is there or deal with the data or something. But whatever happens, we're going to jump to this address in memory. Now JP and JPN are both conditional instructions, and CMP is a comparison instruction. Basically what I wanted to communicate is the fact that comparison instructions and conditional instructions go hand in hand. And when we have a comparison, we have two possible lines of code that can go after that. They can either include a JP or a JPN instruction, based on whether we want to take an action when the comparison is true or false. Anyways, that is pretty much it for instruction groups. Now, to see how these all work, let's move on to an A-level problem. So this is our first A-level question based on assembly language. Here, we've got a program written in assembly. We have the instructions as well as the addresses in memory that they're stored in, side by side. What our task is going to be is to trace this program in this table right here. Now, this may be a bit complicated, but I'll show you what to do. Here we have the instruction address we're dealing with, the accumulator, the index register, and different locations in memory we'll be working with. We also have the output right here. Let's get started. So right here, our first command is going to be LDD365. Now, if we look at data movement, it's a data movement command. LDD means we're going to load the contents of the location at the given address to the accumulator. So the location is 365. And if we go right down here, we can see that at 365, we have the value 1. That means we want to store 1 into the accumulator. So we're going to go right here. We're going to write our address or instruction address, which is going to be 200 because we have 200 right here. And at 200 in the ACC, we're going to put 1 because we want to load whatever is at location 365 into the accumulator. So next, we're going to deal with instruction address 201. Now, if we go to instruction address 201, we're comparing whatever is at 366 with whatever is in the accumulator. That's CMP. So if you go to location 366, we get 3. So we're going to compare 3 to whatever is in the accumulator, which is 1. If they're equal, then we're going to execute this command. But at 366, we have 3. And in the accumulator, we have 1. And they are not equal. So we're not going to execute whatever is on line 202. We're just going to skip over both line 201 and 202. We execute them, but we're not going to show anything on our trace table. So now we're going to move over to instruction address 203. Now at 203 here, we have the increment command, inc. So we want to add 1 to whatever is in the accumulator. Now this inc command is an arithmetic command, and it's used to add 1 to the contents of any register. So here we want to add 1 to whatever is in the accumulator. And we know we have 1 in the accumulator, so that means here we're just going to write 2. Now next we have 204. So right here we have stow 365. Now stow is a data movement command, and stow means store the contents of the accumulator at the given address. So that means we're going to take whatever is in the accumulator and store it at location 365 in the memory. So we're going to go right here, and we're going to take 2 and put it right here. And that's for 204. So next let's take a look at 205. So 205, we want to move. It's MOV. So move the contents of the accumulator to the given register, which is the index register. So we're going to take whatever we have in our accumulator and then move it to the index register. So right now we have 2 in the accumulator. So we're just going to take that and move it to the index register. We're not going to change anything to the ACC. We're just going to leave it the way it is. Now next, let's move on to line 206. So on line 206, it says load x 365. So let's go see what load x is. Load x is telling us to form the address from the address that's specified right here, plus the contents of the index register. So our address, what we're going to get, what our result is going to be, is right here we have 365. And we're going to add that to whatever is in our, hold on, what did it say right here? It said whatever is in the index register. So we're literally going to sum those together. We're going to add those together. And in the index register at the moment, we've got our 2. We've got 2 right here. So we're going to add 2 plus 365, which is going to give us 367. So we have an address, and according to this, we're going to copy the contents of the calculated address to the ACC. So right here, we have the address 367. And if we go to location 367 in our memory, we have the value 65. So we're going to copy this to our accumulator. So that means our accumulator now is going to be 65, right? Yeah, 65. Now next, we're going to go to location 207, which is just output. So we're going to output whatever is in the accumulator. So at 207, we're going to go ahead and in the accumulator right now we have 65. So we're just going to go ahead and output that. And now we'll go to 208. And at 208, we've got jump 200, which means we're going to go all the way back up to location 200 and do this all over again. Now, this is actually kind of like how a loop would work in a higher level programming language. But I'm just going to go ahead and erase the work we did because we're going to have to start all over. Okay, cool. So again, we're going to do load 365. So we're going to load whatever is at location 365 into the accumulator. So right now, actually we're going to write here 200. And right now at location 365, we actually have 2 in the accumulator, or we actually have 2 at 365. I'll go ahead and clean this up a bit. Okay, so we want to load whatever is at 365 into the accumulator. And right now at 365, we have the number 2. So that's going to go into the accumulator now. So I'm actually going to go ahead and write this in red because this is kind of our second cycle through. Okay, so now we're going to go to 201 and we're going to go ahead and let's see what we have here. So we're going to compare 201, whatever is at location 201 to whatever is at location 366 to whatever is in the accumulator. So 366 we still have 3 and in the accumulator we have 2 and they're not equal. So again, we're going to skip this line right here and just keep going. So we've got 201 and 202 and those are both blank and we're going to go to 203. Okay, so now moving on to line 203. So increment the accumulator. So that means, so right now in the accumulator, we've got 2. So we're just going to add 1 to that and we're going to get 3. Remember, this is the accumulator column. And next, line 204, we're going to store whatever's in location 365. We're going to take whatever's in location 365 and go ahead and store that in the accumulator. Let me just double check on that. So store the contents of the accumulator at 365 at the given address. So that means that at 365, right now we have 3 in our accumulator right here. We've got 3. So we're going to store that at 365. So that's going to become 3. Now that we've done that, we're going to move on. And okay, so next we have move IX. So that means we're going to move whatever is in the accumulator to the index register. So line 205. So right now in the accumulator, okay, so in the accumulator, we've got 3. So we're going to go ahead and we're going to store that in our index register. So this is the column for the index register. We'll put that right here. Now, next, we've got load x 365. So what we want to do is we want to take 365 and add it to whatever is, so we're going to add 1 to that, most likely. Actually, let's double check. So load x means Okay, so form the address from address plus the contents of the index register. Okay, so what we need to do is we got 365 right here, and we're going to see what's in the index register. So in the index register, we have 3. So we're just going to add that to 365, and it's going to give us 368. And we're going to go to location 368 right here. We're going to take the contents and store that in the accumulator. So that means for line 206, right here in the accumulator, this is the accumulator column, we're going to write 66. Then we go to line 207 and output. So output the contents of the accumulator. So we're going to output 66 and line 208. Let's go to, so line 208 is going back to 200. So once again, we're going back to 200 right here, and we need to start all over. Now we're going to load whatever is in location 365 into the accumulator again. So now we have 3 at location 365. So that's this right here. So we're going to put that back in the accumulator right here. And right here, we're going to compare whatever is in 366 to our value of 3. So we got 3, and at 366 right here, we also have 3. So they're finally equal. And that means we can actually execute what's on line 202. And that is jump to line 201. So we go right here to line 209, or jump to line 209, and we're just done. That's it. That finishes the program. So I'm going to write line 201 and then 202. These technically don't have any output, but they were executed. And that's basically tracing our problem. Let's go ahead and look at the mark scheme. Okay, so it looks like pretty much everything was correct. We did miss one thing though. Okay, we did miss one thing, and this is actually really interesting. I'll get to it in a second. Okay, so right here at the end we did 201, 202, and we should have actually done 209 because we jumped to 209. We need to write 209 right here. Okay. And one other thing that I want to mention is right here with the output. So we had this line right here, this outline, and it turns out that whenever we're outputting things, whatever value we have there, that's going to be an ASCII code, right? So if we look at our output right here, we have the number 65, but that's actually an ASCII code. I mean, that's how it's going to be interpreted, and that matches the character A. So actually, we wouldn't have 65, we would have A. And right down here, we output 66, and 66 matches B. So we wouldn't have 66, we would have B. That was something great to point out that I actually didn't catch. But in summary, that is our trace table, and that's how assembly works. Okay, so now let's look at a second assembly language example to really solidify our understanding of these concepts. So first, we're going to start at instruction address 77, right here, and that's going to be LDR 0. So that means that we're actually going to be loading the number n after the hashtag into the index register. So for instruction address 77, we're going to add 0 to the index register. Next, we have LDX 110. Now that means we're going to take the address 110, add the contents of the instruction register, or the index register, which is a 0, and we get 110. And we're going to go to this location, which is right down here. We're going to get the value, which is 66, and we're going to put it in the accumulator. If we move on to 79, we need to compare the number 35 to whatever is currently in the accumulator. So 35 does not equal what's in the accumulator. So 35 does not equal 66. So that means that we're going to go ahead and skip 79 and 80 and move on to 81. 81, we're going to add whatever is at address 100 to the accumulator. So if we go down to 100, we have 0 at location 100 in memory. And we're going to add that to 0, and we're just going to stick with 66. So we're not going to change anything, so we're not really going to write anything either. 82 means we're going to take whatever, or we have stow 101, which means we're going to take whatever is in the accumulator and store it at location 101. So actually, hold on. 81 should have been 0. 80, okay. So yeah, 82. We're going to go ahead and 101, we're just going to put 66 right here, because that's currently what's in the accumulator. Next, we have LDM1. And LDM1 just means that we are going to load the number 1 into the accumulator. So line 83, we're just going to have 1 right here, the accumulator. Next, we have add 100, which means, okay, again, at location 0, we still are at location 100. Wait, so it's, yeah, we're on line 84. Let me just write that here. So we have add 100. And at location 100, we still just have 0. Like, we haven't actually done anything with that. So it's not going to change our accumulator, because for add 100, we would take whatever's at 100 and add it to our accumulator. That's still 0. So yeah, just confirming. Okay. Cool. So store 100. Store 100 means we're going to store whatever is in the accumulator at index 100. And okay, actually I'm going to move on right here to 85. So yeah, line 85, store 100. Right now we have 1 in the accumulator. So we're going to store that at location 100 right here. 86, we're going to increment the index register. So that means we're going to add 1 to whatever is the index register. And right now there's a 0 in the index register. So we're going to make this 1. Loadx 110. So with loadx 110, we're going to take 110 and add it to whatever is the index register, which is 1 at the moment. So that's going to give us 111. And then we're going to go down to location 111, which is 65. And we're going to put that into our accumulator. So that means for line 87, we're going to end up with 65 in the accumulator. Okay, so next we're going to go to line 88. And we're going to compare whatever's in the accumulator to 65. Okay, let's see. So we have 65. It doesn't equal 35. But the thing is, right here we have JPN. And JPN is a command that executes when the previous comparison is false. So that means we are going to execute this line. So for line 89, we're actually going to jump back up to 81 right here. And we're going to add 100. So we're going to take the contents of 100. And actually I'm going to write 81 right here because we're going to jump to that. So we're going to take the contents of 100, which right now are actually just 1, based on what we see right here. And we're going to add that to whatever is in the accumulator. So, okay. Add 1, add 100. So we've got 1. We're going to add that to whatever is in the accumulator, which is just going to be 65. So we're going to end up with 66 right here. And we're going to keep going. So right here we have stow 101. So we're going to take whatever we have in 101, and we're going to store that into, hold on. Yeah, we're going to go ahead and we're going to store that in 101. And really that doesn't change because we already had 66. So you can just keep going. So stow 101 means we would take whatever's in the accumulator and store it at location 101. But we've already got 66, so there's really no change there. And then moving on, we're going to load 1. So we're going to LDM1 is just load 1 into the ACC. So that means we're going to go back to 1 being in the ACC right here. And next we're going to have add 100. So if we go to 84, we're going to add whatever's in 100, and that's still 1 to whatever is in the ACC. And that's going to make this 2, because we have 1 in the ACC, and 100 is still, has a value of 1. And okay, go to 85. And we're going to store whatever we have in the ACC at location 100. So that means right here, we're going to put a 2. Okay, and next we're going to increment the index register. So line 86, increment the index register, it's 1, we're going to make it 2. 87, okay, so for 87, what we're going to be doing is we're going to take 110 and add it to the index register, which is 2. So we're going to end up with 112. We're going to go to location 112 right down here, and we're going to get 35 and put that in the ACC. So line 87, we're going to make this 35. And okay, next. All right, so next we're going to have line 88, and we need to compare 35 to 35. But they're equal, so you can skip this line, because this only gets triggered if the comparison is false. So we're going to have 88, 89, and then we're going to load 100. So actually, I forgot what LDD means. Load the contents of 100 to the ACC. So right now at the ACC, okay, right now at location 100, we've actually got the value 2. So for line 90, actually, we're going to load 2 into the ACC. And okay, next we're going to add 48, which means we're going to add 48. We're going to add 48 right here. So we're going to go to line 91. And we have the number 48, and we're going to add that to whatever is currently in our ACC. So we're going to do 48 plus 2, because 2 is currently in our ACC. We're going to end up with 50. Next you have out, so we're going to output whatever was in the ACC. So we're going to output 50. And so this last column is our output. So right here, that's going to be that's actually going to be instruction address 92. So right here, we'd want to, so we're going to output 50, but if we're outputting 50, 50 is just going to be an AS. So we need to find out what the ASCII matching letter is for 50. If you look right here, for 50, the character that gets output is 2. So that means that our output is just going to be 2. And then next, we're just done. That's the end. So let's go look at the mark scheme and see what we got right and what we got wrong. 066, we have 1s, 1, 2, 2, 35, 250, and it actually looks like we are good to go. So let's move on to the second part of this question. So right here, the following instructions are repeated for your reference, and state the purpose of this part of an assembly language program. So we're just going to go ahead and I guess trace this, and we're going to go ahead and kind of figure out like what the purpose of this is. So let's just assume the ACC has a value of 2 in it. So, or let's actually just assume in location 100, right here, we have the value 2. So 100 is just going to have 2 in it. So if we load 100, that means that the ACC, we'll actually write this right here, ACC would be 2. And okay, if we store in 165 whatever is in the ACC, so we'll just put that right here. That means that we're going to put 2 in location 165. But, okay, we'll just get rid of this right here. Okay, but then we have 101. So let's say at 101 we have 3. So, okay, that means that we're going to be loading 3 into the ACC. And we're going to put 3, we're going to store at location 100. So what was here? So we'll store at location 100, 3. And then we're going to take whatever's in 165, so whatever's right here, and load this into the ACC. So we're going to get 2. And then we're going to store whatever is right here at 2. So at 101, we're going to store 2. So that means that now 101 has the value 2, and 100 has the value 3. So essentially what we were able to do is swap between the addresses 100 and 101 using the location 165 as an intermediary, like a temporary storage spot. So state the purpose of this part of an assembly language program. So swap values at location 101 and location 100 and 101. Okay, cool. That's the end of the A-level question. Let's actually just go ahead and check the mark scheme for that one as well. So yeah, swaps the contents of memory address 100 and 101. Anyways, we're good to go. Let's move on to some other concepts surrounding assembly language. Now that we understand how assembly language works, let's talk about how it can actually be converted into machine code for it to be executed by the CPU. So this conversion process is done by something called the two-pass assembler. The two-pass assembler is essentially a program that is used to convert assembly code into machine code. The two-pass assembler consists of 2 stages, each one being called a pass. And broadly, it makes use of something called a symbol table, where the addresses of all instructions, labels, and any data as well are stored. So this is an example of a symbol table. We have symbols representing both different registers, but then we also have symbols representing instructions that are included as part of the code. We also have something called labels. Now, labels essentially are organizational tools for breaking up an assembly language program. In this case, start, loop, and end are labels. And with every label, there is certain code that's associated. For example, with the start label, we'd have this code circled in red associated. Now, we're going to look at each pass individually. So in the first pass, we're going through the assembly language program, examining it one line at a time. And every time we go to each line, we're going through these 5 steps. First, we're going to get rid of elements that aren't essential to the program. So for example, comments. Then we're going to assign a memory location to every line of assembly code. After that, we're going to make sure that every operation code, by operation code, we mean instructions like stow, load, compare, those acronyms that we basically saw in our A-level problems. We want to make sure that these are all part of the assembly programming language, so they're all valid code. After that, we're going to add labels into our symbol table, including the memory addresses associated with the labels. And finally, we're going to get the memory addresses of any instructions associated with labels and put them in the symbol table. That's our first pass. For our second pass, what we're going to do is we're looking at the assembly language program, but we're placing greater focus on each individual line. We're going to use the symbol table we just created in the first pass to produce machine code, which includes both the opcode and operand, so the instruction and anything that instruction is performing operations on, but it's all going to be in binary. So we're basically using the symbol table to produce binary code. Then we're going to store the resulting program in binary for later use, or go ahead and execute it by sending it to the ALU. And those are essentially our 2 passes. So to give you an idea of what object code is, this is basically what it looks like. So this is what we would start out with, and this is what we'd end up with via our 2-pass assembler. So to solidify our understanding, let's take a look at an A-level question. It says tick 1 or more boxes in each row to indicate whether the task is performed in the first pass or second pass of a 2-pass assembler. So removing comments happens in the first pass. Reading the assembly language program one line at a time happens in both passes, although the approach is different in both passes. We're going to generate object code or machine code in our second pass. We're going to check whether the opcode meaning something like stow or comp or anything we saw before, we're going to check whether that's in the instruction set. In other words, if that's part of the assembly language program in the first pass. And it looks like we're good to go as far as the mark scheme goes. So now let's move on to a concept called addressing modes. Now, addressing mode is basically how we deal with memory address locations in assembly language. So in immediate addressing, the operand is directly specified within the instruction itself. So an example of immediate addressing would be something like LDM or LDR, where if we have, for example, LDM 3, then we're just going to be working with the value 3. So we're not referring to an address, we're not referring to another location. We literally know what our operand is, exactly what we're going to be working with. That's immediate addressing mode. Next, we have direct addressing mode, which specifies the memory address where the operand is located. So here we have an example of direct addressing. There's a lot more examples, but here when we have LDD followed by some address location like 165 or something like that, that's going to be direct addressing mode. Next, we have indirect addressing mode. So with indirect addressing mode, we're using a register to hold the address of an operand. So the instruction specifies a register containing the memory address. So if you look at indirect addressing right here, we didn't really work with this in our previous examples, but right here, for example, you have LDI followed by an address. So you might have LDI and then the address 165. It says the address to be used is at the given address. Load the contents of this subsequent address into the ACC. So that means that we would go to 165 in our memory, and there we might have another address like 105. And then we would get the data at this address and then send that to the ACC. So you can see why it's indirect. Now next we have indexed addressing mode, and this is the LDX that we've seen before. This involves using the base address and an index. An index actually, in this case, an index register in order to calculate the actual address of the operand. So remember, if we had an address 165, we might add it to IX or index register, And then we're going to use that to get some value. So if you get 167, then we're going to go ahead and get whatever value is there and then do whatever we want with it. Basically, the idea is that we have some index value that's held in another register. And again, in the case of A level, that was mainly in the index register, especially with the LDX command. So we get an address and we get an index stored in a register. We put those together to get the address of the actual piece of data that we want to work with. That's index addressing mode. And finally, we have relative addressing mode. The operand specifies a value relative to the current instruction's address, usually as an offset. I didn't really have a good example of this, and that's mainly because we don't really see it in our A-level programming language, or A-level assembly programming language. Basically, we're going to specify some value that has a relationship with the current, with an address, or that's an offset, and then we're going to use that to get some data. And that's about it for subsection 2. Let's move on. Now, our next section is going to be subsection 3, which is on bit manipulation. Let's get started. In this subsection, we're going to cover bit manipulation operations and binary shifts. And we're going to illustrate these concepts using A-level problems. Now, the content in this subsection is part of the 15 to 20 points on paper 1 that we referred to in previous sections. So let's get started with bit manipulation operations. So when we're talking about bit manipulation operations, we're literally talking about operations that are done in assembly language. So right here we have a list of opcodes that are a part of the assembly language, and we have different operands they can work on. So these opcodes represent symbols you've actually seen before. So these are connected with logic gates and logical operations, which we've looked at in previous units. Now what we're basically going to do is we're going to apply these logical operations to either denary numbers, binary values, or a value at some address. These two right here are slightly different. These are binary shifts, which we're going to talk about later. Anyways, to see how this works, let's go ahead and look at an A-level example. So right here, the current contents of the ACC are this 8-digit binary number. We need to show the result after the execution of the following instruction: XOR, and then another 8-digit number, which is in binary, as symbolized by the B at the beginning of the statement. So right here. So we have XOR. And if we go back to our truth table right here, this is what an XOR gate looks like and a truth table. So if we just kind of look at the truth table, we see that anytime the inputs, both inputs are 0, are the same, we get 0, and when they're different, we get 1. So we'll just write that here to give us, or just kind of jog our memory. They're the same at 0. If they're different, it's going to be 1. Okay, cool. So what we're going to do now is we're going to compare every single digit from left to right, and then write the output right here. By compare, we're going to apply the XOR operation. So we're going to go one by one. Now, our first value is 1 in the accumulator, and the matching value is 0 right here. And they're different, so we're going to write 1. Next, we have 0 right here and 0 right here, and they're the same, so we're going to write 0. We have 0 right here and 0 right here, and they're the same, so we're going to write 0. We have 1 right here and 1 right here, and they're the same, so we're going to write 0 again. Now here we've got 0 and 1, and they're different, so we're going to write 1. 0 and 1, and they're different, so we're going to write 1. 1 and 1, they're the same, so we're going to write 0. And 1 and 1, and they're the same, so we're going to write 0 again. Let's check our answer, and looks like we are correct right up here. So that's basically how it works. You're basically applying logical operations to each individual digit in one binary, in basically the first binary value and then the second binary value. The first binary value being right here, and the second one actually being the operand in the assembly language operation. Seems pretty straightforward, but let's look at a few other examples. So right here, the current contents of the ACC are this value right here, and this value right here. So we're comparing that to the operand right here. And these are being compared using an AND operation. So we're going to AND these values in the accumulator with these values in this operand right here. So let's go ahead and let's refer to our truth table. So we've got AND right here. The only situation which we're going to have a 1 is going to be when we have 1, 1 is the input. So we're going to go ahead and recreate the truth table right here. So 0, 0, 0, 1, 1, 0, and 1, 1. And all these are going to be 0, except for this one right here. So what we can do is compare each individual digit. We have 1 and 1, which is going to give us a 1. We got 0 and 1, 0, 0 and 1, 0, 1 and 1, 1, 0, and okay, so we have 0 and 0. So we've got all the rest are going to be 0, 0 or 1, 0. So these are all just going to be zeros because none of those are situations in which we'd have a 1. Let's go ahead and check our answer, and we are good to go. Next question. Now next we've got a similar problem. We've got some contents in the ACC, and we've got an operand right here, 8-digit binary number. This time we have OR. So again, we're going to go through the same process. Go to our OR gate right here. And the only situation in which we have a 0 is when both inputs are 0. So we've got 0, 0, it's going to give us 0. Everything else is going to give us a 1. So let's get on with it. 1, 1, that's going to give us a 1. 0, 1, it's going to give us a 1. 0, 0 is going to give us a 0. 1, 0 is going to give us a 1. Let's see, 0, 1. It's going to give us a 1, 0, 1, 1. Okay, the rest are just going to be 1 and 1 because we're not going to have two zeros. Let's take a look at the answers, and I think we're good to go. Let's double check actually. Yeah, we're good to go. Now the next concept we're going to look at is going to be binary shifts. Binary shifts basically refer to moving around the digits of a binary number in some direction or the other according to some logic, depending on the type of shift that it is. The first type of shift we're going to talk about is going to be a logical shift. This is where the digits of a binary number are shifted left or right by a certain number of positions. So for example, if we have 0, 0, 1, 1, or 1, 0, 1, 1, 1, 1, and we do a logical shift, let's say we do a logical shift to the right by 3 digits. That basically means that we're going to move, we're basically going to get rid of these 3 digits, right? We're going to end up with 0, 0, 0, 0, 1, 0, 1. Well, actually, no, we got 3 zeros. So 0, 0, 0. And then this is going to be all that's left on the right side. So this basically ended up right here. So we moved all the binary digits over by 3. And as a result, we ended up losing the last 3. And we added 3 zeros to the left of the binary number. And that's just an example of a logical shift. An arithmetic shift is similar, but we're shifting the digits of the number while preserving the sign, duplicating the sign bit. So for example, if we had the same value, so we had 0, 0, 1, 0, 1, 1, 1, but we had an additional, actually I guess we had a 1 right here. We had an additional sign bit, which was 0, and this was our sign bit, then that would stay the same. So we would just, or actually let's just make that 1. Let's make our sign bit 1, right? So that we have a sign bit of 1, then we are literally moving everything except for the sign bit. So we would have 1, and then 0, 0, 0, 0, 0, 1, 0, 1. So basically everything we have here, but the sign bit would just stay the same and not change. And then we have a cyclical shift where we're moving the bits of a number to the left or right, wrapping the shifted out bits around the opposite end of the number. So for example, if we had 0, 0, 1, 0, 1, 1, 1, 1, and we were doing a cyclical shift, then we might, if we're just moving by like 2 bits, then what we might do is we're going to keep this. So we're going to say 0, 0, 1, 0, 1, 1. But then these 2 bits right here would be wrapped around to the other side. So they would be right here. So actually, I'll just put that in a different color. And that's going to be an example of a cyclic shift. Now, by far, actually the only type of shift I was able to find on the A-level exam was the logical shift. But you should know what all of these are. Anyways, let's take a look at some A-level examples to really solidify your understanding of this concept. So right here it says the current contents of the ACC are this. Show the result after the execution of the following instruction. So if we go to our table of commands, right here we have LSR, and it says bits in the ACC are shifted logically n places to the right. Zeros are introduced on the left-hand side. So we're basically shifting these digits to the right. And because we have a 2 right here, we're shifting the digits 2 places to the right. So let's just make sure. Yeah, logically n places to the right with n being right here. So what we're basically going to do is we're essentially just getting rid of these. We're shifting everything to the right. So we're gonna have 0, 0, and then whatever this is right here. So we're just gonna have 1, 0, 0, 1, 0, 0, and that's gonna be our answer. So let's check. So I guess this was actually number 4 right here. So you got 0, 0, 1, 0, 0, 100, and we are correct right there. So again, LSR is going to be shifting to the right, and we have LSL, which is shifting to the left. And that basically just means moving everything over to the right by 2 places, and that's also going to mean getting rid of the last 2 values. And our empty spaces right here, after getting rid of the last 2 values, are just going to be 0. So the next thing we want to do is we just got another similar problem. It says the accumulator currently contains this binary number. Write the contents of the accumulator after the processor has executed the following instruction, LSL 2. That means we're going to move everything to the left by 2 places. So we're basically going to get rid of the leftmost values right here, and we're going to introduce zeros on this side. So we're going to end up with 1, 1, 0, 1, 0, 1, 0, 0. And let's go ahead and make sure that's correct. And we are good to go. Okay, cool. So now let's take a look at our last question. So right here it says, identify the mathematical operation the following instruction will perform on the contents of the accumulator. And this operation is LSR3, meaning we're shifting 3 bits to the right. So that means we're going to get rid of these last 3 bits, and we're going to end up with 0, 0, 0, and then these 5 numbers right here. So that's going to be 0, 0, 1, 1, 0. Now, basically what's happened is if we think about this in denary terms, this was to the power of 0, to the power of 1, to the power of 2, to the power of 3, to the power of 4, and to the power of 5. We've gotten rid of the last 3. So we're basically taking these last 3 digits. So these are our new last 3 digits, so these digits right here, and we're reducing their powers. So now this is going to end up as to the power of 2, to the power of 1, and to the power of 0. Now this essentially means that we're dividing the value of our original number. So the original number in the accumulator, we're dividing that by 2 to the power of 3. And this may be kind of difficult to wrap your head around, so I'm going to explain this to you in denary terms. So let's say we have the number 100,000. Okay. Now, if you just look at converting this to, well, if you just look at this in terms of decimals, right, or bases, we have 10 to the power of 0, 10 to the power of 1, and then 2, 3, 4, and then 10 to the power of 5. Now let's say we shifted this 3 bits or 3 digits to the right, similar to what we've done right up here. We would end up with 0, 0, 0, 100. Now what that essentially means is that we're going to go from 100,000 to 100. So we're going to be dividing 100 by 100,000 by 1,000, which is going to give us our end result 100. Now 1,000 also happens to be 10.3. Does this make a little bit more sense now? So in this case, we would be dividing by 1,000. In this case right up here, we'd be dividing by 8. So the mathematical operation will be dividing the original number. If we check our answer, it looks like that's the correct answer. Anyways, this brings us to the end of our video. Now to close out this video, I would like to share some channel updates specifically pertaining to my series for the A-level exam. At the moment, I'm working my way through paper 1, and that means that the next topics I cover are going to be ethics and ownership, communication, and data security. In my opinion, these are some of the low-hanging fruit of the paper 1 curriculum, and this is probably what I'll be able to cover before the A-level exam, but we'll see. Now, I know some of you have asked about paper 3 pseudocode and paper 4 as well, basically the programming components of the A-level exam. And unfortunately, I won't be able to get to those before this exam. Instead, I plan on creating an online course or 2. By online course, I really just mean a series of videos with some resources in order to address these. And these will probably be something that you would have to pay for because they do take a ton of time to cover with sufficient detail and accuracy. Anyways, I hope you enjoyed this video, If you'd like to see more like it, please remember to like this video and subscribe to the channel. Have a nice day and good luck!